So as you may see in Blackboard, we have updated 3 files. There will be 2 Python files and 1 NumPy archive files. You can download it right now. I think one of the real beauty of this course is that you start from the really basic stuff. I mean, low-level stuff. Remember Lab5, we had to do some like GCD, calculator, RTL, whatever. And today, finally, we are doing some AI thing. So is there any students who never heard about AIP2 course? I've never used PyTorch or TensorFlow in my life. Raise your hands. Never? You know what a DNN is? Okay, sure, that's good, great. Actually, for hardware developers, DNN is some bunch of matrix multiplication stuff, which we are exactly going to do today. I remember that Lab5, the assignment was to make a floating point version matrix multiplication hardware, which is the underlying operation of DNN models. So today we have 2 goals. First, we will use the IP from our Lab5 assignment to accelerate one of the DNNs, very simple DNNs. Secondly, we will learn about quantization, about how we can trade off accuracy to make better hardware. So let's get started. So I think everybody can open like your local desktop. This does not require to be run on PYNQ boards. Guess everybody has like Python installed, right? If not, please install it right now. And I'm pretty sure you guys would know how to install TensorFlow. Sorry, PyTorch. In the mnist_train.py, I made a very simple mnist train code. So let's start to understand this. We have a bunch of, I don't know, import whatever. So basically, PyTorch allows us to install this, like download the MNIST dataset. MNIST, as we learned from AIP2 course, is one of the most basic and easiest dataset we can use in DNN training. So basically, these 2 lines are just the lines to download the MNIST dataset from the internet and just load it to PyTorch. You see another variable called the batch size, which is in DNNs, it is very common to use batched learning and batched inference, which basically instead of running a single inference iteration at a time, we'll just make a batch of 50 images to compute at once. So this is just PyTorch syntax. You don't have to know all the details from it, but let's see. So we have some data set ready, and we have the optimizer, which is just basically DNN stuff to train the DNN. If you go to the line 50, we have model.train. And the model is actually defined here. So let's try to understand this. So one of the most simplistic DNN models is the MLP. Is it MLP? Yeah. So MLP mostly consists of multiple linear layers. Linear layers meaning basically you have a matrix multiplication layer followed by a nonlinear activation, and that kind of repeats. In this case, we have a very simple 3-layer MLP model. Self.fc1, fc2, fc3. So you see at the first layer, if you look upon the MNIST dataset, I'm pretty sure you have looked at once, but the input of the MNIST dataset is a grayscale image of 28 by 28 pixels. So you have a 28 by 28 image, which has a grayscale, meaning that the pixel values are somewhere between 0 to 256. So we will get this as the first input, and that's why the size of the first linear layer is 784, which is actually 28 cross 28. So what do we have here? Then we have 128, meaning that the first layer has 784 input neurons and 128 output neurons. Remember the dimension of your Lab 5 homework? What was the dimension for the Lab 5? 128 cross 64, right? So that will be used to accelerate the second layer. Right? The second layer is a fully connected layer which has a 128 input neurons and 64 output neurons, which in operations, we will do a 128 cross 64 matrix multiplication. Obviously, this can be accelerated using the Lab5 IP. And then we have the last layer. You see the output neuron have 10 neurons, which means that each neuron will represent a class. Class meaning that the handwritten digits should be somewhere 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 classes. Between each linear layers, if you see the forward function, we have a hyperbolic tangent function. I made that just because it's just like one of the simplest activation function possible. And then after the fully connected tree layer, we have the softmax. I'm pretty sure you guys know softmax. It's kind of the smooth version of argmax function, which we mostly use in classification DNN algorithms. So, okay, very simple DNN model. And usually, if you're using an MLP, especially a fully connected layer, you have an extra bias term, which is exactly the same as satisfied. You have a AX plus B, which is the bias term. But however, this is the most simplest MLP model possible. We have 3 linear layers. And here is actually the loop for the training. We prepare the data from the train loader, which is the MNIST loader. And we do some backward, calculate the error, and update the weights. And we do this 4 times, 4 epochs, meaning that we will train the data set 4 times. It's 4 because I just wanted to make it simple. You can increase that if you want. Anyway, after training the model using PyTorch, we save the model. And this code is just for convenience. I made this code that you will allow us to transform the PyTorch model format into NumPy format. So let's use this. Okay, so we get an accuracy about 90%. You can run it right now. Can you please try to run it? Run the code. Run this code. It should work, right? Okay, so going back, after you have once run the train code, you should have the model.mpy, which is the PyTorch model converted into the NumPy format. So I actually made one more code, which is the MNIST inference. So basically, let's assume that you are using a hardware accelerator. Doesn't care whether it's like TPU or RIP or whatever GPU you use. So basically, if you want to make use of your custom hardware, you need a software called the runtime, right? There should be some sort of host code that calls your GPU. For GPUs, it's usually written in CUDA. And in our case, we'll be using the Jupyter laptop of the PYNQ board in Python, right? So my point is that we need a line of code that actually calls our hardware to run the DNN inference. And this is the code. So As I told, a DNN model is just a bunch of matrix multiplication in addition with nonlinear operations. So you can directly translate the PyTorch code into something like this. So basically, the MNIST original.mpy is the original MNIST data set stored in the NumPy format. And this is just X and Y, which loads the input and the labels from the MNIST data set. And if you load the model.npy, you can figure out the weights here. So FC1W, 2W, 3W corresponds to the weight of each layers, which we can proceed to write a forward function like this. Imagine we have an x0, input of x0. X0 should have a shape. Can you guys see this, like letters here? Is it readable? Okay. Shape of what? Batch size and 28 by 28, right? So if you actually look upon the shape of each layers, the first layer has an input shape of 128 cross 784. Usually, in matrix multiplication, it's more convenient to store the weight in a transpose format. So this is actually a question you can think of yourselves. You see, the first layer has an input activation of 784 and 128, which correspond matrix multiplication of input x weights, and the weight should have a dimension of 784 and 128. But usually, this is stored in a transpose format. And the reason because of it is usually transpose matrix multiplication is faster than naive matrix multiplication. You can think of why. So this will actually affect your hardware design. You can think of why. So using the same reasoning, the FC1W has 784 input neurons. Oh, sorry. With an output neurons of 128. But the shape is 784, 128 cross 784. And you see the input have a shape of batch size by 784, meaning that actually the matrix multiplication should be a transpose operation. This should correspond to a matrix multiplication of batch size 784 times 128 cross 784 dot transpose. I'm pretty sure you guys took the undergraduate linear algebra. Is there any student who did not understand this? Okay, fine. So we have done the matrix multiplication for the first layer. Now let's see our model definition here. We have, a hyperbolic tangent. So we have a hyperbolic tangent. And then the second layer, if you see the output of the first layer, let's just print it out. So print something like shape of A1 equals 2 np dot shape A1. Oh, it's 100 cross 128. The 100 should be the batch size. So A1 has a shape of batch size cross 128, obviously. So that's why the second layer do a matrix multiplication looking like this. And then we have the second activation, which then feeds into the hyperbolic tangent. And then we have the last matrix multiplication layer. If you compare the definition of both two, you see that there is one operation here that is missing. What is that? What's missing in the inference code? Softmax. We don't have a softmax here. Why is that? Yeah. Okay. You know the output values of 10 neurons. What's the answer of your classification? What's the results? You see the values of the last layer. What's the classification results? Guys, you took AIP2. What's the results of the classification? The one with the highest value, right? The one with the highest value. So that's why we actually do not need softmax. Softmax is just a smooth version of argmax, which is just picking the one with the highest value. And that's why at the below loop here, we will say, oh, find the maximum value of the results. And if it's correct result, we will count this as a correct result. And that's how we can actually compute the accuracy. So let's see. In the train code, we had an accuracy of 90%. Oh, we have an accuracy about around 93%. Why is it higher? Because in the train, we only evaluate on the test data set, but the 92% is for the full data set, which is 70K images. So summarizing, we trained the model in PyTorch, and we replicated the code on MNIST, which can be ran on the PYNQ board. You guys can guess what to do next. Right now, use this code, upload it on your PYNQ boards, and instead of using NumPy on the second layer, NumPy will use the CPU cores, use your Lab5 custom IP to compute the second layer. Is there anybody who cannot understand this? You will copy and paste this code on your PYNQ board, and instead of using NumPy for the second layer, use your custom hardware IP to run this. Do you understand? Okay, let's start now. Okay. Guys, we will proceed to talk about quantization. I know that at least 2 teams kind of succeeded in running PYNQ boards with using the hardware version. Okay, the assignment till next week is that you will make a better version of Lab5 assignment using quantization and more sophisticated programma optimization. And next week, you will make a presentation about how you partially accelerate your MLP design. Do you understand? The final project of this course is to accelerate every layer of the DNN network using the PYNQ boards. And you can think of tomorrow's next week's presentation as kind of a rehearsal to the final project presentation. Do you understand it? Okay, so before we proceed, I need to talk about quantization today. Okay, so does anybody remember how much resource utilization you have on Lab5 assignment? How much FPGA board utilization you have? Open up HLS, open up the report, how much utilization? Is it high? Yeah, but like anyway, like how much utilization are you using? Utilization. Resource utilization. You can find it on the implementation reports. Yes. Flip-flop, FF, how much? 13. LUT, how much? 37. BRAM, how much? 14. 14? 14. So meaning that you're using approximately half of the FPGA space, right? Like, I don't know, like maybe half or like less than half. Which means that if you use unroll and pipelining and you parallelize the hardware more, you can actually get better speed up, right? But there's one trick to put more keys on your hardware. For example, you're using floating point 32, meaning that you're using floating point 32 multiplication and addition. How much utilization for the DSP? 4. So you're not almost using it, not using the DSPs. Okay, but anyways, so basically, a FP32 multiplier is about 2.5 times more than the int32 multiplier. And the int32 multiplier is bigger than the int8 multiplier by how many times? An int32 multiplier is bigger than an int8 multiplier by how many times? I mean, like, just guess it. It's either 2 or 4. Or like 16, I don't know. So 32 is 4 times the bit width of 8. And since it's a multiplier, it's actually 16 times bigger. Meaning that, going the opposite direction, if you change your hardware from floating point to int32, you get 2.5 times more PEs. 2.5 times better peak utilization. And if you change your int32 hardware into int8, you have 16 times more peak performance. Do you get it? Do you understand? Using smaller PEs and smaller bit widths will make a better hardware design. But the problem is, how are we going to use DNNs then? You see, let's get back to this inference code. Get back to the inference code. So right now, every operation is done with floating points. For example, let's print out A1. Okay, it's all floating points. And I see that the values are somewhere between -1 to 1. Seems reasonable, right? So what if I change this number to integers? What will happen? Let's say I'm just doing something like it's all zeros. Does not make any sense. So the goal is that we want to run this DNN model with integers. And how are we going to do that? Double E guys, raise your hand. Electrical engineering. Everybody heard Xinxi? You heard Xinxi? Yes? What's the concept of SNR? Signal to noise. What do I need to do here? Why is it all zeros? The signal is too small. And how can I improve it? What should I need to do? Amplify them, correct. How about I multiply a big constant, I don't know, 256. Oh, we have better result than before. Okay, so instead of floating point operations, I will make a quantized version of activation and weights. And this will be something like same for FCW2. And instead of this matrix multiplication, will it be correct? Oh, it seems correct. But actually, there's one pitfall that we need to scale it back again, which means that we need to divide this something like this. And then now we have the correct results, right? Because we multiplied them, we need to divide it back to 256. So if you were to work with integer hardwares, actually, unlike floating points, integer hardwares has an upper limit and lower limit that it can actually, what do you say, like express. So let's say we are using an int8 hardware. What's the maximum of int8? Assigned int8. Mingun, what's the maximum of assigned int8? Int8. Is it 128 or 127? Oh my God. It's 127, bro. And what's the minimum? Minus 128. So what I'm gonna do is that I multiply this as some sort of big constant, and I need to cast it. I forgot the how to cast NumPy. Cast. What was it? Clip? I think it was clip. Yeah. Oh, max and min. So dot clip minus 128 to 127. And in this way, I can expect every activation to be somewhere between the int8 value. Using the same reasoning, I can actually make the matrix multiplication to clip to the int8 value. And when I use the results back on software version, I actually need to change the type as something like this. Oh, I get correct results. Nice. How about I use some weird scale factors? You know, this scala we are multiplying is called a scale factor. We get incorrect results. So remember, this is a 10 classification. So if the results are below 10%, it's worse than just random guess. So my point is that a very simple naive quantization works this way. You kind of get a better approximation about your distribution, and you multiply some constant. And if you can, however, increase the SNR, you get nearly the same performance as a floating point version. You see, even though we used int8, we get 93%, which is almost close to a floating point baseline. However, you need to use the correct scale factors. What if I reduce the bit width until, like, I don't know, int4? What's the maximum value for int4? You sure? Yes. In case of int4, you go from 7 to minus 8. Now let's go something like this. Oh. Well, that's quite bad. I'm just guessing random numbers here. Oh, it's still bad. One better way is that you can use the mean value of A1 and W1. You can do something like A1 divided by the mean of A1. And you can make this, I don't know, like 3 times. Well, and of course you need to like scale it back again, but I'll just like ignore it right now. And oh, it's even worse, I think. I don't know why, but it's worse. Still doesn't work. But anyway, you can do quantization, something like this. And actually, if you search through the internet, you get a lot of research about DNN quantization. Actually, we used to write good DNN quantization papers. See? Anyway, one good example of DNN quantization is binary neural networks. If you can somehow figure a way to quantize the neural network with only -1 and 1, which are binary values, you can actually reach at near performance to the floating point baseline. This is a 2015 paper. And in binary neural networks, you can even replace the tangent H function to just a sine function. And one of the beauty of binary neural networks is that you don't actually need a multiplier because it's binary values. You only need addition. And that's why binary neural networks can reach a lot better performance compared to the floating point version, even on CPU and GPUs. And you can even think of better version of binary neural networks such as something like this. Okay, so going back, I really want you guys to have a better concept of neural network training, and you can actually try to search on the web to find better algorithms to how to quantize the DNN network. The assignment for next week is that still you will be only accelerating the second layer of your DNN model. However, you can use various methods to quantize your layer. And you will try your best to reach the best performance as you can. And next week, here, we'll have a presentation for each of the groups. Am I clear? You have any interesting questions or something, whatever, related to quantization? If you're done, we're done here. Okay, see you next week. Goodbye.